All right. So the challenging thing with solving differential equations is typically when we find the antiderivative, we usually only have been working with the right side, right, or one side of the equation. We take the antiderivative of y prime, it becomes just y on the left side, and we've always just dealt with the right side. But now with differential equations, we're going to have to kind of work on both sides of the equation, take the antiderivative. So it's going to feel like multiple problems within the same equation. And then the algebraic steps required to solve for y sometimes can feel a little long. So this is a big topic on AP exam. So we're applying the same antiderivative rules as before. It's just going to feel a little bit longer because we have to work on both sides. Okay, so the first thing we do is we separate variables. Okay? We rearrange equations with y and dy on the left side, x and dx on the right side, and we're basically splitting this into two separate problems. So what I like to do is I like to just cross multiply. If I cross multiply, I may not get a full separation of variables, but I will get all my denominators kind of out of the way. Okay, so it says solve the differential equation. So the whole idea, again, differential equation just means a derivative, something in the derivative level. And solving just means you're trying to get that derivative back up to the function level. So you're just taking the antiderivative. So the first thing here, we're going to just go ahead and cross multiply here. So it may not get everything sorted out the way we would like, but it will. I think it's easier for students to work with something that doesn't have a denominator. So cross multiply, we get y dy is equal to 2x dx. Okay, so we have to first decide whether we have full separation, and we do because x's are all gathered together, y's are all gathered together, the y and dy together, x and dx are together on the same side. So now, next we're going to take the antiderivative of both sides. So every time you do this, you're basically treating this like two separate problems. So you're going to find the antiderivative in terms of y on the left side, and then in terms of x on the right side. Okay. So what's the antiderivative of y? Y squared over 2 plus c. Okay. On the right side, 2x dx. What does that become? 2x squared over 2, and then plus c. Okay. Any questions so far? Now, both sides are producing plus c, but typically what we do is we just group all the c's together and put it all together on the right side. So y squared over 2 is equal to x squared plus c. Okay, I'm going to multiply 2 to both sides of the equation. So after we get through the calculus, the cleanup is usually just trying to get the left side as minimal as possible. Can you get it all the way down to y? So here I'll multiply both sides by 2. So get that 2 to go away from the denominator. The right side, distribute the 2 through, I get what? 2 x squared plus what? Plus 2c. Now, what do you know about 2c? Still a constant. So we typically just leave it as C. I mean, it's not wrong to put 2C, but we know that C absorbs all coefficients and constants. So anything that is still a constant, we can just kind of represent it as a constant. Okay, we could take the square root, do plus or minus, but we'll save that for the next problem. All right. But typically, once you get past the calculus, the rest of it is just trying to get that left side as cleaned up as possible. Okay. So again, differential equation just means something that is at the derivative level with an equal sign in between. And then solving it just means trying to get it out of the derivative up to the function level. Okay, in terms of y and x, no longer with the dy and dx in place. Okay. All right. Number 2, dy dx equals x times 1 plus x. Sorry, x times 1 plus y. Typically, if a problem is presented to you with parentheses, they're trying to help the student. They're trying to show that the parentheses are there to help you separate where it needs to be separated. So if they give you something that's in parentheses, you typically want to hold on to it. If you lose it, if you distribute, you may have a harder time grouping things that's supposed to be grouped. So the parentheses are actually here to help us group things and separate things a little easier. Okay, so again, I like to just go ahead and cross multiply just to get that denominator dx out of the way. So I'm going to put this over 1. I'll do cross product here. Okay, so 1 dy is equal to x 1 plus y dx. Everybody okay so far? So what I want us to make sure that we understand is that another reason that I like to cross multiply is I may not have full separation yet, but I do have dy dx locked in. So you want your dy and dx on separate sides and in the numerator. Okay, so that's important. Your dy dx's have to be in the numerator. It's okay to have x and y's in the denominator, but your dy dx needs to be in the numerator. Now, we want separation of variables. We want y and dy together. We want x and dx together. What's the one thing that you see is out of place? The 1 plus y. Okay. So what can I do with that 1 plus y? What can I do to bring it to the other side? Say it again. How would I move that 1 plus y to the left side? What's the operation that I can do? Division, right? Divide, right? So I'm going to divide. These are all being multiplied. So the way I undo multiplication is through division. So I'll divide both sides by 1 plus y. Okay, so now we have full separation of variables, y's and dy's on the left, x and dx on the right. It's okay to have y's in the denominator or x's in the denominator. We just have to make sure our dy, dx's are landing in the numerator. Okay. So the right side is just power rule. The right side is just power rule, right? But the left side, we have to go through a little bit of what? U substitution. Okay, what's our U value? 1 plus y. Okay. So it should be a pretty straightforward here, 1 over u du. Once I make my substitutions, right? And what's integral of 1 over u du? Yeah, natural log absolute value of u. Plus c, but we're going to leave that plus c on the right side. Let's just go ahead and finish this up. Replace the u back in terms of y. So natural log absolute value of 1 plus y. Equals. What does x become? X squared over 2 plus c. Sorry, I think I meant to drag 3 down a little further because we need a bit more room to finish off number 2. But if we bleed into number 3, it's okay because we can just put the work for number 3 below. But we're done with the calculus. We've technically solved this differential equation because we've gotten it out of the derivative level and we brought it up in terms of x and y. Okay, any questions? Now, the only thing left is we have to solve for y, right? And y is stuck inside this natural log. So the way we undo natural log is we involve the inverse. What's the inverse of natural log? Exponential function base what? Base e. So what we can do is we can raise both sides with e as the base. And so now we're in the cleanup stage. Okay, we've solved it. Now we're just trying to find a way to rearrange this equation to get a y by itself. The y is stuck inside natural log, so we raise both sides with e as the base, and that will allow this to go what? To do what? To cancel, and I'm just left with what? Absolute value of 1 plus y. Okay. Now I have e to the x squared over 2 plus c. Now, both of these are sitting where? Up in the exponent. Okay, so I want to make sure that we understand that we've raised everything up. It's sitting up in the exponent. And there's a property that I want us to know how to do. So if I have a base a raised to the m plus n, I can split this up into a to the m times a to the n. There's something that we can do to clean it up using this method. So I'm going to treat the x squared plus 2 and plus c as two separate exponents, and I'm going to split it up as the product of two separate bases. Okay. So e to the x squared over 2 times e to the c. Right, so here's the reason why we want to do that. E to the x squared plus 2, that's an exponential expression. What's e to the c? It's still a constant, right? It's just because e raised to any number is still a number. So now I can represent this whole thing as a c, but now it's being multiplied with what's before it. Okay. So typically what we do is if we realize that c is just multiplied with an expression, we typically like to pull it out in front as a leading coefficient. Okay. Now the absolute value represents that plus or minus values can be represented. So what I'm going to do is I'm going to drop the absolute value and bring that plus or minus over to the other side. Okay. To adjust for the fact that absolute value represents plus or minus. Okay, now c can be both what? Positive and negative values. So I can just let this plus or minus get sucked into that c. And I can drop the plus or minus because c represents all positive and negative values. And now finally I can solve for y. What can I do? Subtract 1. Now I can't let that 1 be inside c because it's being multiplied. So the c and the negative 1 doesn't get absorbed into that c because it's part of a different expression. Okay. So this is a very specific process, but I just want to introduce this algebraic cleanup to you. We'll do many more of this. Right now, I just want you to follow along and understand if you feel like you understand the steps that I'm going through. Okay, let's go to number 3. Find the general solution for 2x plus 3y y prime equals 0. Then find the particular solution if the solution passes through the point 1, -2. So let's not worry about this particular solution. Let's just focus on the general solution. So that just means we want to solve the differential equation. So first thing I like to do is just go ahead and replace that y prime with a more descriptive form. And y prime is the same thing as dy dx. I'm going to get it to a place where I can cross multiply and go through those steps. I'll just go ahead and subtract 2x to the other side. And I'm just rearranging so I can kind of line things up and work towards cross multiplying so that I can separate, work towards separating my variables. Again, cross multiplying doesn't guarantee that your variables are separated, but it's nice to look at an equation without having to worry about the denominator. And if you haven't moved anything, you're just having to divide something over to the other side. Now, are the variables separated? Yes, x dx together, y dy's together. We could go ahead and take the antiderivative, but here's something that I would suggest is that if there's anything that you can move to the right side, that would just mean less work down the road. Okay, because eventually everything has to come to the right side anyway. So if something doesn't have to be on the left side, I'm going to go ahead and move it to the right side. Okay, so what doesn't have to be on the left side? That 3, right? So I'm going to go ahead and move that 3. It's not wrong if you leave that 3 on the left side, but eventually you're going to move it over. So I'm going to just try to do as much as I can before as I see things that can be moved. So I'll divide that 3 over. That will just be in the denominator of my coefficient. And again, I like to have my coefficient sitting in front of my variable and not below it. It just feels easier. All right, so now antiderivative, y dy, integral -2/3 x dx. Okay, so once we're here, we're really treating this like 2 separate problems. We have to do a process for y on the left side and do a process for x's on the right side. All right, so y becomes y squared over 2. Plus c, yes, but I'm going to go ahead and just save that plus c for the right side because we're going to group it all together on the right side. Okay, -2/3 x becomes x squared over 2 plus c. Okay, can I clean this up any more on the right side here? 2's cancel out. Okay. So technically, we have the general solution. Next step, we want to solve for c,
But I'm going to just try to clean up a little bit more here. I'm going to multiply both sides by 2. But once your plus C shows up, you can decide when to solve for C at any moment in time. You can wait till the end. You can start, once that C shows up, you have a lot of options in terms of when to solve for C. But I like to solve for C when my equation looks a little cleaner. I could wait till the square root shows up, but if the square root shows up, then I got to deal with the square root. So I'm going to just see if I can resolve C at an equation that feels the most simplistic. So at this point, I'm going to go ahead and solve for C. Right? But you don't have to. And because students may be solving C's at different points, your C's may show up as a different value halfway through. But in the end, when everything is said and done, our C's will match up. But because your C's if you're solving for C earlier or later, it may be different than what I have, which is fine as long as we end up in the same place. Okay, so 1 goes in for X, -2 goes in for Y. The whole purpose is to solve for C. Once we solve for C, we can update the C equation, and I can kind of move forward and try to solve for Y. Okay, so 4 plus 2/3. So that's 12 over 3 plus 2 over 3. So that's 14 over 3. So I'm going to take that C value. I'm going to update. Right, there's a bunch of C's here, but I want to put it in for where I started making my substitutions. Oops, sorry. That's just Y squared, not Y squared. Okay, we're almost there. We've resolved the C, but I still want to solve for Y. So what's my last step here? How can I get Y by itself? Take the square root. Now, when I take the square root, what's going to pop up in front? Plus or minus. Okay. So what I want us to understand is that these are two separate solutions. These are two separate solutions, but we want the solution that has this order pair as part of the curve. Okay. So we only want to choose the one that is part of the curve. Sorry. One is the positive, the other is negative. Okay. So the question is, how do we know which one to choose? So the easiest way to decide which one to choose is to look at the Y value. Okay. If I plug in a 1 in for X, the only way this can produce a negative value is if there's a negative sitting in front, right? Because I can't have a negative inside the square root and it'll never show up. So if you're having to choose between plus or minus, look at your order pair and look at the Y value. Whatever the sign of the Y value is the sign that you want to keep. So if the Y value is positive, then you'll choose the positive square root. If the Y value is negative, then you choose the negative square root. But the big idea here is that I got to be able to find an equation that has this order pair as part of the curve. All right, so if I plug 1 in, I'm never going to get -2. So we know that 1, -2 is not part of this first curve. So look at the Y value if you're deciding between plus or minus square roots. So the particular solution will pass through this order pair. So therefore, we select this particular solution because we have this as a requirement. Okay, any questions? Let's see. Okay, so I want to see if I can spend some time starting the quiz review. Again, this is not going to be on the quiz, but we're kind of and we'll spend a lot more time kind of building and getting comfortable with these steps as part of us solving differential equations.
It's the last quiz. But we don't have it.
Oh, no.
Okay, so in your packets, before I go into quiz review 2, or page 9, which is quiz review 1. Okay. I want to talk about page 7, where we have the list of rules that we've accumulated since first semester. Okay. So let me go through these here. So we first semester, first thing we learned was derivative power rule. And then we learned the 6 trig derivative rules where we lined up our 2 columns and sine, tangent, secant, cosine, cotangent, cosecant. And we learned all these derivative rules, and we know that these are very important also because this is how we get to our trig integrals, right? So these 6 trig derivatives can be turned into trig integrals simply by moving from the right side to the left, right? It's because, right, so cosine's antiderivative must be sine, or if the sine's derivative is cosine, then cosine's antiderivative must be sine. So we see that here, right? And hopefully we're comfortable with these trig integrals because we're just working backwards from the trig derivatives. Okay. And then we see a lot of pairing that we learned. E to the u's derivative is e to the u times u prime. So therefore, the antiderivative of e to the u is e to the u plus c. Natural log of u is u prime over u. If we work backwards there, the integral of 1 over u du is natural log s value plus c. We also talked about how this is the one condition that the power rule is not able to handle. So we're able to use this rule if we're stuck with power rule not being able to work out. So we talked about how if I bring that u to the top, u to the -1 will become u to the 0 over 0. Any other power, I can do power rule, but this u to the first in the denominator, we have a special rule that's the natural log absolute value of u. And then we also, yesterday, we also learned the derivative of a to the u is natural log of a to the u times natural log of a times a to the u times u prime. So if I take the antiderivative, I have this new rule here, 1 over natural log of a to the u plus c. Okay, now you don't have to worry about this one here. This will not be on any of the quizzes or tests. So we briefly talked about that there are 6 trig integrals that came from the 6 trig derivatives, but then there are 4 additional ones that involve natural log, and we need to be responsible for these as well. So if you notice, these trig antiderivatives don't show up in our trig integrals, right? I don't have one for tangent or secant or cotangent or cosecant, okay? But they all involve natural log. Okay, so that's why they're grouped together in this unit, in this natural log, in this log and exponentials unit. So this is the way that I remember these rules. I know that first off, I know that tangent doesn't show up in one of the 6, so I know that's got to be a natural log one. So the way I remember it is, I think of a tangent as sine over cosine. And because of u substitution, if I were to go through this problem, I would let the u value be cosine. Cosine becomes negative sine. So I know that cosine is what's going to show up, because if I'm going through a u substitution problem, if I treat it like a sine over cosine, I will choose the denominator as my u value, right? And so that's why if I understand that cosine is in the denominator of tangent, that's why it's going to show up in my rule. Right? And then cotangent produces cosine over sine, or cotangent is cosine over sine. And because sine is in the denominator, that's why it shows up in my natural log rule. And the way I remember secant is that, well, I know secant is not part of the original, so it has to be natural log. And I know that secant tends to have secant and tangent involved. So I just remember it's a little bit different. So natural log secant u plus tangent u. And the cosecant has a similar pattern. Because cosecant and secant, they always kind of go hand in hand in terms of their pattern. So we know cosecant isn't one of the original 6, so it's got to be a natural log. And cosecant and cotangent usually goes together. So negative natural log cosecant u plus cotangent u. And now the final thing is the negatives, right? How do we remember the negatives? And I just saw this this pattern that may be helpful to you, is that trig integrals, you want to look at what's produced. Okay, so if something produces something that starts, if a trig integral rules produces an antiderivative that has a c near the beginning, then that is what's going to have a negative in front. Okay. Now derivative is a little bit different, right? Derivative is if it starts with c, then it'll produce a negative derivative. With the trig integrals is if a c shows up in my rule on the right side, then it's going to have a negative. And the same thing here with the tangent and the cosecant. You see how tangent has a c near the beginning, so that helps remind me that there's a negative in front. Cosecant u produces a c that is near the beginning, so that is also a negative. But I will say this, a lot of students get these two mixed up because they see the cotangent, and I think we tend to associate cotangent with negative. So the negative, students tend to put negative for this rule, and tangent, students tend to associate tangent with positive, so they get these signs mixed up. But if you can look at the result and say, okay, if something has a c on as my, if I could produce a c in my answer, in my antiderivative, then I'll put a negative in front. So maybe I think that will be helpful in helping keep track, because I think this is what throws students off the most, the tangent, cotangent, and the negative and positive there. Okay, so these are the rules that we'll be responsible for, and we're kind of building things from first semester as well. Okay, so let's go to page 9. If you're working ahead, the key is on page 14. Okay, but let's just, well, spend a minute looking at the rules again, if you want, on page 7. But once you're ready, see if you can recall these rules, because hopefully we can do this today, and we'll do this tomorrow, and then Wednesday morning for the Thursday morning for the help session, you can kind of drill yourself through these rules. Okay. Okay, so the first one is power rule.
Second one, this is the one case that power rule is not able to handle. E to the u. We tend to have an easier time with this. We know e to the u is just e to the u. This is the one rule that is just itself. And then I'll go to a to the u. A to the u looks a lot like e to the u, but then there's a bit of conversion that has to happen with natural log. And these are the four new ones. So tangent, the way I remember tangent, again, is I know tangent is sine over cosine. And I know it's going to be the cosine that shows up in my rule. I see a letter C show up near the beginning of my rule, so I know I'm going to put a negative in front. Cotangent I know is cosine over sine. I know it's going to be the denominator that shows up in my rule. Natural log absolute value of sine of u plus C. I don't see a C near the beginning of my antiderivative, so I'm not going to put a negative in front. Secant is not one of my original six. It's going to involve natural log. Secant and tangent, they usually go hand in hand, so that helps me remind me. But I know the derivative rule is secant tangent. This one's a little bit different. This is secant plus tangent. I don't see a letter C near the beginning, so I'm not going to put a negative in front. Right, cosecants, similar format. Cosecant, cotangent usually goes hand in hand. I see the letter C near the beginning of my integral rule, so I'm going to put a negative in front. Right, we'll practice this again tomorrow. Okay, let's look at number one here. Dx over 2x plus 3. I can also think of this as 1 over 2x plus 3 dx, if that feels more familiar. There's more than one term in the denominator. I can't split this up. I can't just do power rule. I have to go through use substitution. There's too many terms in the bottom. What could be our u value? So I'm hoping that after I clear everything out, that it will match one of these rules that I can use. What can I do with that too? Push it out in front as a 1/2. Once that coefficient is out of the way, you should be able to get a clear match with the rule that you want to use. Right? It's got to look exactly like it, and it does. Okay, so natural log. Place the u back in terms of x. Okay. Number two, too many terms in the denominator. We can't split it up, can't do power rule, can't expand. So what's our, or separate, sorry. What's our u value then? Yeah. And is that x going to be taken care of, you think, down the road? Because the degree is good, right? X squared will produce an x. There may be some leftover coefficient, but it's okay. We just have to keep track of it. Okay. Okay, so no homework tonight, but I'd like for you guys, if you have time, to start working through these review sheets. I have more than enough than I have time to do in class. So try to work through these.
to get a head start with your quiz review. The keys are attached on page 14 and 15. And tomorrow we'll devote our whole period to quiz review. All right, come up and get your phones. The bell schedule is on the board.